Okay, we're moving on into chapter 8. Chapter 8 today, talk about the moon and Mercury. Just before we get into that, I just wanted to point out, I'm sure you're already aware of this, but grades are, of course, posted on the class website. And the average here was about 78, about what I expected. So let's see, that's around the D range. So again, they're there, just listed by the standard code numbers that I used. Okay, so we finished up everything through chapter 7. And we've talked about the Earth, so now we're kind of moving on to the section of the course where we talk about all the other planets in the solar system. And we also are going to talk about various moons in the solar system and the formation of the solar system and the sun as we finish out the semester. Okay, so you probably recognize the moon here, hopefully. This is the side of the moon that we actually see from Earth. So this is the side that always faces us. And this is Mercury. So just, there's a very sort of straightforward kind of similarity between the moon and Mercury. They both have these gray, highly cratered surfaces. Now, this photo happens to be from the mid-1970s from one of the Mariner missions, which flew to Mercury. Those particular missions actually did not go into orbit around Mercury. So what happened was there were two flybys of the Mariner mission, flew by Mercury, but did not go into orbit. And coincidentally, all times it saw the same side of Mercury. So until the latest mission got there, which is about a year ago now, called Messenger, we didn't even know what the other side of Mercury looked like, just to give you an idea that we're still in the early phases of understanding our own solar system. So we'll talk more about Mercury Messenger. But anyway, as I said, we see some obvious similarities between the moon and Mercury. They're both heavily cratered, one thing, very dark surfaces. They have what we call a low albedo, which is a low kind of reflectivity of radiation back into space, so they look dark. When we look at them, we can see that there's no atmosphere. There's no clouds or anything like that. There's no atmosphere at all, and there's no liquid water at all. They're both completely desolate worlds with essentially barren surfaces and near perfect vacuums instead of having any kind of atmosphere. The moon is a little bit smaller than Mercury, not too much smaller. There are some internal differences, as we'll see. Mercury actually does have a very substantial iron core, like the Earth, and the moon does not have a core like that. So although we see similarities on the surface, there's some differences on the inside, which indicates that they have different formation histories. True messenger, that's a typo there. Let me fix that. There is no such thing as the moon messenger. Second, sorry. Can't trust your call these days. Maybe do it yourself. There we go. So this again is a shot of the moon from the Mariner mission. And this is a shot from Mercury Messenger. It's not actually a single shot, it's thousands of photos that were done because the Messenger mission actually is in orbit around Mercury. It's the first time we've ever put a spacecraft in orbit around Mercury. So it's completed hundreds of orbits of Mercury over the last year. I've taken thousands of photographs and they've been pieced together. So now for the first time, we're actually able to see really high resolution and true color images of the entire surface of Mercury, which is going to kind of revolutionize our understanding of the formation of terrestrial planets because we've never really been able to see these details. Yes? Well, okay, Mercury is around 0.4 astronomical units out or so it's rather close to the sun. But, of course, the satellite was obviously designed to withstand thermal heating at that distance. So there's really not too much of a problem with that with a properly designed spacecraft. It's okay. Yeah. We'll see that it's actually a much larger challenge to study Venus, as it turns out, particularly if you want to land on the surface of Venus. But this is not a mission that actually lands on the surface. It's only one that's orbiting. Anyway, let me just... I'm going to go back further. start there? Here we go. Let me just show you the website real quick for this. Okay, so again, you can see here over 170,000 images, all kinds of stuff. It's actually been in orbit 956 days, so actually it's a couple of years now already. And it's a nice science gallery that you can look at, lots of different images, things like that, lots of different information about the mission. So the point again of this particular mission is that we did not ever even have a complete mapping capability, but this particular satellite is going to do a lot more than just take pretty pictures of the surface. It's also going to actually detect a lot more details about the magnetic field and things like that that reveal properties of the internal planet. Okay, so as we work our way out against the solar system, it's kind of interesting to look at this plot once in a while because we see Mercury there and our moon right there. So we can see that our moon is obviously smaller than Mercury. Our moon's about a quarter the size of the Earth. So the Earth would be about 4 times larger than the moon, about this size. So if the Earth is that large, and the Earth is about more than twice the size of Mercury. But there are other moons in the solar system that are actually larger than Mercury. So it's basically the smallest planet. Now that Pluto has been demoted, not considered a planet anymore, it makes Mercury the smallest planet, and it's actually smaller than a couple of the moons of Ganymede, here, a moon of Jupiter, and Titan, the moon of Saturn. And this is actually a very interesting object because, as you can see, it's shrouded in cloud. It's the only satellite that actually has a dense atmosphere like that. Okay, so talking about the moon, we're going to kind of focus on the moon and Mercury and different similarities. Of course, it's the only natural satellite of the Earth. There's hundreds of man-made satellites and small rocks and things in orbit, but it's the only large natural satellite. Really completely desolate, no atmosphere, liquid water, nothing like that. We are going to find that there's no liquid water, but there is actually quite a lot of ice. In dark, deep craters on the moon, there's quite a lot of water ice, which is shielded from direct sunlight and shadows. And that ice is predominantly at the north and south poles of the moon. And that actually could be a source of liquid water for human colonies in the future. Now, without any atmosphere, we're able to see something that would take place on the Earth if we had no atmosphere, which is this very extreme temperature variation between noon and midnight. The moon is essentially at the same distance from the sun that the Earth is, because the moon's orbit is about 237,000 miles out from the Earth, but the Earth is 150 million kilometers away from the sun, so the moon and the Earth are essentially at the same distance from the sun. So if we had no atmosphere on the Earth, and we didn't have the atmosphere providing this thermal blanket, which gives us some continuity of temperature, we would be seeing temperature variation just as strong as what we're seeing here on the moon. A temperature over 400 kelvins at noon and only 100 kelvins at night. I mean, that's way, way, way below the freezing point of water, which is like 273 kelvins. So just 300 Kelvin variation in daily temperature is what we would actually experience on the Earth if we didn't have the thermal moderation provided by our atmosphere, also by our oceans as well. But here in the middle of the continent, where we are, basically the atmosphere providing this thermal continuity. So the moon doesn't have that, so the moon's daily temperature cycle is this enormous swing between above boiling point down to below freezing point. And of course, these lots and lots of craters, which are due to asteroid impacts, very well preserved. The crater evidence has been preserved for millions and perhaps even billions of years because of the lack of any kind of liquid water or atmosphere that would cause erosion, as we see happen on the Earth. Okay, we've actually talked a little bit about the moon's orbit already earlier in the semester, but we see the moon orbiting the Earth about once per month, essentially. It's actually a 27.3-day sidereal orbital cycle. We do see the moon keeping the same face toward the Earth, so that was known, since the history of mankind. Anytime you look up at the moon, if you can see the full face of the moon, you're going to see the same features, sort of man in the moon kind of features. So the moon is actually spinning with a rate that equals its orbital rate, or to say its spin period is the same as its orbital period. So it spins once every time it orbits us. And because it spins once every time it orbits, it's always keeping the same face towards us. The plane of the lunar orbit is tilted 5.2 degrees with respect to the plane of the Earth's orbit around the Sun, and that, of course, is the reason that we don't have eclipses every single month. We have this idea of eclipse season, which is going to occur when the Earth is along this, what we call the line of nodes, which is the intersection line between those two planes. There's also rather, sort of a significant eccentricity to lunar orbit, about 5.5% eccentricity. Now, the way this works in terms of variation of distance is that if you take the eccentricity and double it, you get the percentage of variation of the actual distance. So we see about a 10% variation of the distance of the moon from the Earth, and this is what gives rise to things like annular eclipses. Remember, when you get an eclipse, a solar eclipse, if the moon happens to be farther out in its orbit, then its angular size is a little too small to cover the sun completely, and what you get is a little ring of sunlight around the moon, which is the annular eclipse. Well, that wouldn't happen if it weren't for the fact that we have a significant amount of eccentricity there. And that, of course, changes the perigee and apogee distances from each other. You can actually see that if we compare these two numbers, they differ by about 10% or so. So the apogee distance is farthest from Earth, perigee distance is closest to Earth. And so these numbers correspond in miles to about 237,000 miles. And we also have the moon actually obeying a version of Kepler's laws as it orbits around the Earth. It's going to sweep out equal areas in equal times. So this means that the moon actually moves a little faster at perigee than it does at apogee, just as we saw with planets orbiting the Sun. Okay, so again, the sidereal period, 27 to 23 Earth days. That, in other words, would be the time between alignments between the Earth, the Sun, and the Moon and a distant star. Okay, actually not the Sun, just the Earth, the Moon, and a distant star. When we reachieve that alignment, one sidereal month later, okay, that's the 27.3 Earth day period of time here. Now, if we're talking about the time between full moons, and here we started actually with a new moon, right? The moon is between the Earth and the Sun, so that's a new moon right there. This is not a new moon yet right here because the Sun's down there. So this is like a third quarter moon as seen from the Earth. We have to wait a little bit longer for the moon to orbit around far enough to actually give us another new moon, which is when the moon is between the Earth and the Sun. So this occurs, as we say, one synodic, or solar month after the starting point. So if we start at the starting point here, which is 0 time, then one sidereal month later, which is 27.3 Earth days, we have realignment with a distant star. But we have to wait from the beginning, 29.5 Earth days, to get realignment with the Sun. So we're usually mostly interested in this 29.5 day period because that's the period that dictates the time between light phases. You know, like here we're talking about 2 new moons, right? Start with a new moon there. The next new moon is going to be 29.5 of our days later because that's the synodic period measured with respect to the Sun. All right, so just a figure from the book showing the same idea. Sidereal month here is indicated by these dashed lines being parallel to each other, which means that they're lining up at the same distant star.